Welcome to this webinar. Thank you very much to the South Wales Materials Association, the SWMA, for hosting us today. And we have some QR codes that they'd like me to share, which are on the screen here to sign up to their mailing list if you're not already, and also links to some to sign up for membership as well. Well worth it. I've been a member for a while, and it's brilliant resource and support network. So let's see. So yeah, today we're going to talk about the hydrogen economy. My name is Dr. Nathan Cooze. I've been at the university for over 15 years in various research roles in metallurgy, mostly in corrosion of next generation galvanized steel alloys, but also including some work with hydrogen embrittlement in low carbon steels. More recently, I've been focused on the teaching aspect of things as part of the Net Zero Skills team here at the university, mostly focused on upskilling the workforce towards the net zero transition. So the aim of this taster session is to introduce the hydrogen economy and to give you an idea of what's in our full online hydrogen economy course. This is an online 10 credit course. And I believe links will be shared in the chat as we go through. And if you have any questions as we go through, please do put them in the Q&A section, and I'll try and cover some of those at the end. Hydrogen is increasingly seen as a versatile energy carrier that can support the transition to a low carbon energy system. It can be produced using a range of technologies and energy sources, including renewable energy. And emerging hydrogen technologies are enabling new ways to store energy, decarbonize industry and power sectors that are difficult to electrify, such as heavy transport and high temperature industrial processes. I'm going to briefly cover some climate change. I'm not going to dwell too much on it, but just to set the scene. To start with, a quote here from the UN Secretary General. He says that out of all the challenges that he faces, none are so large as climate change. He says it's an existential threat for most life on the planet, including and especially the life of humankind. As you're probably aware, the increase in carbon dioxide emissions and other gases can be closely correlated to global warming. And this graph here shows the global average temperature and the carbon dioxide emissions over the years 1000 to 2000. And we can see that they rise sharply after around 1800 or 1850, along with rising global average temperatures. To try and slow this process down, you may be aware of the Paris Agreement, which is a legally binding international treaty on climate change made by the UN and adopted by 196 countries in Paris in 2015. And its primary goal is to limit climate temperature increase to 2 degrees Celsius in this century and achieve a climate neutral world by 2050. A rapid transition to low or zero carbon energy sources has been identified as key to achieving this goal compared to pre-industrialization levels, which is 1850 to 1900. So let's check how we're doing. This graph contains a little bit more up-to-date data, and it shows the annual global mean temperature anomalies relative to the 1850 to 1900 average. And this is shown on the x-axis from 1850 all the way to 2025, which so it shows we are still continuing with this upward trend with the increase in temperature, but for the most part we are still under the 2 degrees threshold for now. And the actual average temperature globally in 2025 was estimated to be just over 15 degrees Celsius. And this was increased from 14.3 degrees in just the year 2000. So 25 years has increased nearly by a degree. So yeah, we still got a lot of work to do. If we look at global greenhouse gas emissions by sector, we can see that electricity and agriculture make up half of all emissions. and the remainder then is built up of buildings, transport, other industries, and including other energy industries as well. If we pick up on the steel industry as an example, this makes 20% of annual industrial energy consumption, whereas the steel industry itself is responsible for 7% of the world's total carbon dioxide emissions. So in blast furnace or traditional basic oxygen steelmaking, for example, the carbon dioxide emissions are typically 2 tons of carbon dioxide per ton of steel. With the natural gas direct reduction of iron or DRI process with electric arc furnace steelmaking, these emissions are typically reduced to 1.4 tons of carbon dioxide per ton of steel. If we were to use a scrap-based electric arc furnace steelmaking process, the emissions are typically reduced a lot further to 0.4 tons of carbon dioxide per ton of steel. And further advantages of arc furnaces are reduced cost of steel production and reduced energy requirements. So there is a need really for fossil-free steel in order to help achieve net zero. But how is all this relevant to hydrogen? In order to realize fossil-free steel, we need to develop new ways of iron and steel making, which mainly may include replacing the blast furnace with a cleaner alternative. Massive changes are needed to achieve net zero steelmaking. A key step is to replace carbon with hydrogen, which is technically feasible, but it is essential that the hydrogen is generated using renewable energy. Otherwise, power generation using fossil fuels is counterproductive in terms of reducing carbon dioxide emissions. The IEA, or the International Energy Agency, predicts that 15% of steel will be produced by hydrogen in place of carbon by 2050. And I'll talk a little bit more on this process later on. For now, I'm going to play a short video. This is from our team here at the university, and this is just an overview really of hydrogen. This one and many other videos are available on our YouTube channel as well.
Hydrogen, the fuel of the future. In a world grappling with climate change and declining fossil fuels, a beacon of hope emerges. Hydrogen. This once humble element, the most abundant in the universe and on Earth, is found in water molecules, plants, and animals. Hydrogen holds the key to a cleaner, brighter future. Our journey begins with the science of electrolysis. Air, water, the most common molecule on Earth, is transformed into hydrogen fuel using renewable energy like solar or wind power. Wind and solar, nature's gifts, become the driving force for hydrogen production, making it a sustainable fuel source. While electrolysis reigns supreme, scientists are exploring diverse pathways to hydrogen production, pushing the boundaries of innovation. Once generated, hydrogen needs a safe haven, from cavernous underground storage facilities to next-generation materials. Researchers are developing efficient and secure solutions for this versatile fuel. Transporting hydrogen across vast distances requires ingenuity. Pipelines crisscrossing continents, ships navigating the seas, and innovative carriers emerge, ensuring hydrogen reaches where it's needed. It fuels zero-emission vehicles, powers homes and industries, and even finds applications in aviation and space exploration. From fields to factories, skies to kitchens, hydrogen's reach extends far and wide, painting a picture of a clean and sustainable future. The possibilities are endless. As we embrace hydrogen, we embrace a future powered by clean energy, innovation, and deep respect for our planet. The future is bright, powered by hydrogen. Hydrogen.
Okay, so very positive spin on hydrogen. I'll be covering a couple of different aspects in this presentation as we go on later on. It's not all blue sky. Hydrogen is an energy carrier and can be produced from a wide variety of sources. And the market is well established, with global demand currently standing at 8 to 10 exajoules, most of which is consumed in the chemical sector. At present, over 95%, sometimes almost 99%, from what I've been reading, of worldwide hydrogen production comes from fossil fuels at the moment. Hydrogen from renewables can be produced from various pathways, with the most established being the use of renewable electricity to split water into hydrogen and oxygen in an electrolyser. As the video mentioned, hydrogen is being used as an alternative fuel that can be produced from diverse domestic resources. Although the market for hydrogen as a transportation fuel is still in its infancy, government and industry are working towards clean, economical, and safe hydrogen production and distribution for widespread use in fuel cell electric vehicles, or FCEVs. These vehicles are now available in limited quantities to the consumer market in localized regions domestically and around the world. And the market is also developing for larger vehicles, buses, material handling equipment such as forklifts, ground support equipment, and medium and heavy duty trucks, as well as marine vessels and other stationary applications. Just to cover these briefly, some main advantages of hydrogen. Firstly, is that it's abundant in our environment. Green hydrogen is considered to be carbon neutral or clean, and also hydrogen has the potential to decarbonize heavy industries. And it's also good for storage due to high energy density when compressed. However, one challenge of using hydrogen as a fuel is efficiently extracting it from its compounds and the harmful emissions during extraction. But clean hydrogen is currently in sort of work in progress type thing. It's currently very expensive to produce, and there are efficiency issues with extracting, storing, and also utilizing hydrogen as well that need to be considered. The current hydrogen market, hydrogen production is currently valued at over $120 billion per annum and is anticipated to grow by 5% annually over the next 5 years. The market demand is usually met by the pyrolysis of hydrocarbons to produce something called grey hydrogen, which we'll come on to in a second, which results in high levels of carbon dioxide emissions. The main uses are oil refining and fertilizer, and about half of it is used to produce ammonia, which is then used directly or indirectly as a fertilizer. And agriculture and the world population is growing, therefore ammonia demand is also growing. Ammonia can also be used as a safer and easier indirect method of transporting hydrogen. Transported ammonia can then be converted back again to hydrogen. The other half of current hydrogen production is used to convert heavy petroleum sources into lighter fractions suitable for use as fuels, and the latter process is known as hydrocracking. Currently, global hydrogen production emits 900 million tons of carbon dioxide per annum. So I started to mention the different colors almost of hydrogen so far, and this is a short video just explaining how hydrogen is classified in industry.
When hydrogen burns, it generates energy in the form of heat, with water as a byproduct. That means energy created from hydrogen generates no atmosphere warming carbon dioxide, making it one of the many potential energy sources that could help reduce carbon emissions and slow global warming. But creating hydrogen and transforming it into a useful format requires energy, and that energy is not always necessarily renewable. That process is also inefficient and expensive compared with other forms of energy, renewable or otherwise. Producing hydrogen takes energy because hydrogen atoms don't exist on their own. They're almost always stuck to another atom often another element. In the energy business, people generally refer to hydrogen by an array of colours as a shorthand for how it was created. Although this serves a purpose, it's not an ideal solution because it doesn't indicate how much carbon was produced in order to obtain the hydrogen. Firstly, green hydrogen is when the energy used to power electrolysis comes from renewable sources like wind, water, or solar. Electrolysis is used to split the water into hydrogen and oxygen. Blue hydrogen is hydrogen produced from natural gas with a process of steam methane reforming, where natural gas is mixed with very hot steam and a catalyst. A chemical reaction occurs, creating hydrogen and carbon monoxide. Water is added to that mixture, turning the carbon monoxide into carbon dioxide and more hydrogen. If the carbon dioxide emissions are then captured and stored underground, then the process is considered carbon neutral, resulting in blue hydrogen. Grey hydrogen is made from natural gas reforming in the same way as blue hydrogen, but without any efforts to capture the carbon dioxide byproducts. Pink hydrogen is made from electrolysis powered by nuclear energy, which does not produce any carbon dioxide emissions, although nuclear energy creates radioactive waste, which must be stored safely for thousands of years. Yellow hydrogen is hydrogen made with electrolysis from the energy grid. The carbon emissions vary greatly depending on the sources powering the grid. Finally, turquoise hydrogen is produced from methane pyrolysis, or splitting methane into hydrogen and solid carbon with heat in reactors and blast furnaces.
Okay, so yeah, lots of different ways that you can extract hydrogen, and they're often classified with by color scheme. And sometimes you could really consider the hydrogen as a Swiss Army knife, Swiss Army knife of the future global economy. It's able to do pretty much any job that needs doing. There's so many applications that it could be applied to. However, the problem is, just like potentially a large Swiss Army knife, you wouldn't use hydrogen for everything that you could theoretically do with it. Clean hydrogen will have to win its way into the economy case by case. It could do so on merits, or it could do so because of supportive policy, for example, including carbon prices in that. But it will have to do so in competition with every other clean technology that could solve the same could solve the same problem. And that is where the dreams of this hydrogen economy hit reality. And in almost all cases, there is a good reason why hydrogen is not currently used, because other solutions are cheaper, simpler, safer, more efficient, or just more convenient. On this slide, I've got a hydrogen ladder, and this can help to identify where hydrogen is most likely to play a key role in a net zero future, and where other solutions may be more practical. And you can just see from this slide that there are so many different applications which we could use hydrogen for, but it might not be suitable in all cases. It's an attempt to put the cases for clean hydrogen into a logical form, I suppose. And I saw this presented by Michael Liebreich, and the source references are on the slide, into some sort of merit order because they're not all equally likely to succeed. So what the ladder does do is summarize in a simple graphic a view of where clean hydrogen is sure to be part of a net zero future. If we start at the top, we can see the sectors such as chemicals, like fertilizers and methanol, industries such as shipping, steel manufacturing, and long-term storage. Here, we currently already use grey or polluting hydrogen, so a switch to cleaner green hydrogen is almost inevitable. If we look towards the bottom of the ladder, sectors such as local trains and buses, light aviation, and also domestic heating, in these instances, there are almost certainly other and better solutions, for example, direct electrification and batteries to make hydrogen uncompetitive. And yeah, of course, what it does do is bring together all the different factors which will decide success or failure of a clean hydrogen solution. These can include thermodynamics, micro and macroeconomics, safety, the human behavior, resilience, and geopolitics. It's complex. It is a complex process, and there will be regional variations as well. However, the ladder here does just present a single global view, really, just to give you an idea. The hydrogen is seen as a complementary source of energy to renewable energy sources such as solar and wind power. Projects aimed at improving biomass growth, harvesting, and handling to reduce the cost of biomass resources, for example, used in hydrogen production are ongoing. And whilst steam methane reforming is already carried out commercially, other processes such as thermochemical water splitting, biological and photoelectrochemical processes are in early stages of lab development and considered potential pathways for the long term. However, the primary focus of research currently is on the use of electrolyser technology. Although hydrogen is one of the most abundant elements, as mentioned, in its pure form, it is not widely available. Hydrogen needs to be extracted from compounds, and hydrogen is, as a versatile clean burning fuel, has a huge potential. So in September 2020, we saw the first hydrogen-powered train on UK's railways and the development of hydrogen fuel cells to power lorries. Currently, almost all hydrogen for industrial processes is extracted from compounds such as methane and is then classified, as either grey hydrogen, blue hydrogen, or green hydrogen, depending on how it is extracted. Grey hydrogen is produced from natural gas via reforming, generating hydrogen and carbon dioxide, with around 10 kilograms of carbon dioxide emitted per kilogram of hydrogen. It's currently the most common and cheapest method, but of course has significant environmental impacts. Blue hydrogen is the same process as grey, but it also adds in the carbon capture and storage to reduce emissions by up to 90%, although this does add cost and further complexities. Green hydrogen, produced by electrolysis using renewable electricity, is the lowest carbon option, but is currently very limited due to high costs and availability of renewable energy capacity. We look back at the steel industry again. Currently, hydrogen could be used to replace granulated coal injection in a blast furnace, which would reduce carbon emissions by 20%. But it is not carbon neutral because of the need to use coke as a reductant. Hydrogen could also be used to produce direct reduced iron for supply to an electric arc furnace, leading to a carbon neutral production process, providing that green hydrogen was used. DRI in an electric arc furnace is currently considered to be one of the most viable options and the long-term solution to achieving carbon neutral steel production, especially in Europe. As mentioned, grey hydrogen is the most common form of hydrogen used in industrial processes. It's extracted from compounds with carbonaceous byproducts and is mainly produced through steam methane reforming. In addition to this, the carbon monoxide is produced as a byproduct. Steam reforming is a catalytic process which converts hydrocarbons and steam into hydrogen and carbon oxides, followed by key steps including syngas production, water gas shift, and gas purification. We're not going to go into those today. Feedstocks typically include natural gas and light hydrocarbons, with a desulfurization step required to protect the catalyst. The process then increases hydrogen yield and removes carbon dioxide, therefore producing high purity hydrogen. Carbon dioxide emissions can be significantly reduced through a process of carbon capture and storage, which is where blue hydrogen comes in. It's the same as grey, but it has this carbon capture and storage, or CCS, process at the end to reduce emissions. As a result, it has a lower environmental impact, but there are limits currently to the CCS technology and its economic attractiveness. An alternative approach is carbon capture and utilization, or CCU, although applications for this remain limited. And let's have a little look now at carbon capture in a bit more detail with a short video.
Carbon capture is one possible route to not only cleaner steel making, but also cleaner energy production. In fact, carbon capture is even being considered as a means of vacuum cleaning the broader atmosphere. Waste flue gases usually contain other gases besides carbon dioxide, such as hydrogen, carbon monoxide, nitrogen oxides, and methane. In a simple carbon capture technique, waste flue gases are intercepted before they exit to the atmosphere. Carbon dioxide is separated from other gases across a filter by spraying with a carbon scrubbing chemical, such as calcium carbonate. The scrubber binds with the carbon dioxide, which is restrained to the filter while the other gases are emitted. Under the application of heat and pressure, the scrubber is separated from the carbon dioxide. The scrubber is collected and can be reused. The carbon dioxide is collected and injected deep underground to be stored in porous rock, or can be used to make chemicals such as methanol by mixing with hydrogen.
So, hydrogen transportation. Hydrogen, of course, like most or all fuels probably, can be transported through pipelines or other means similar to natural gas. And large networks are already planned across Europe, including around 150,000 kilometers, linking countries like Italy, Austria, and Germany. However, the challenges such as hydrogen embrittlement and leakage must also be addressed or considered. A lot of research and work going on in this area, in particular innovations like ArcelorMittal's grade of steel for their pipes are helping to improve pipeline safety and reliability by giving a resistance to hydrogen embrittlement. Underground gas storage for hydrogen is not straightforward, as there are several considerations. For example, pressure of stored gas is different at different points at the cavity. Generally, pressure increases with the depth of the cavity, and this gives rise to minimum and maximum levels that need to be controlled. The minimum pressure limit maintained towards the surface is to avoid the cavity from creeping over time. And in other words, the minimum pressure must be maintained in order to maintain the structure of the cavity and to avoid the gas from escaping. Whereas the maximum pressure limit maintained towards the bottom of the cavity is to avoid rupture at the bottom of the borehole and cavity. So we talked about blue hydrogen, and that could support early growth of the hydrogen market, as most hydrogen today is produced from natural gas. We could retrofit these processes with carbon capture and storage, allowing existing infrastructure to be used while reducing emissions, helping to meet steady industrial demand as green hydrogen scales up. However, this does have limitations. It still relies on finite fossil fuels. It's exposed to price volatility. It does not fully eliminate emissions, and it faces cost and public acceptance challenges around carbon storage. Among the different various shades of hydrogen, green hydrogen that are produced from renewable energy is the only suitable one really for a fully sustainable energy transition. The most established technology option for producing this is water electrolysis, fueled by renewable electricity. However, other renewable-based solutions to produce hydrogen do exist, but these, except for steam methane reforming with biogases, there are no real mature technologies at commercial scale yet. So that brings us on to green hydrogen, which through electrolysis is consistent with the net zero route and allows exploitation of synergies from sector coupling, thus decreasing technology costs and developing flexibility to the power system. Low solar and wind power costs and technological improvement are decreasing the cost of production of green hydrogen. So for these reasons, green hydrogen from water electrolysis has been gaining increased interest. The missing element in the acceptance of green hydrogen as a preferred product of the future is a viable, cost-effective means of production of hydrogen using renewables. Electrolysers are the technology necessary to produce hydrogen using electricity and water as inputs. And it's a well-established technology that is deployed mostly in the chemical industry. And while scale-up is needed to bring costs down, technological innovation is also needed to further improve performance of the technology, that is, efficiency and plant lifetime. This can be done via things like new catalysts and configurations, the standardization of designs, and a move to mass production of the equipment. And green hydrogen is still 2 to 3 times the cost of blue hydrogen at the moment. The cost of the former is defined by electricity costs, investment costs, fixed operating costs, and the number of operating hours. The investment cost dominates as it is spread over a small amount of hydrogen. And the electricity cost becomes dominant as the number of operating hours increases.
Electrolysis of water using a solid-state polymer electrolyte membrane (PEM) is the preferred method of green hydrogen production. The electrolyser cell consists of several key components. Firstly, 2 end plates, which are usually fabricated from titanium. The PEM is placed between the 2 end plates. The PEM is typically fabricated from a sulfonated tetrafluoroethylene-based polymer, which is solid material of 0.2 mm thickness. The PEM serves to carry protons from one electrode, namely the anode, to the other electrode, namely the cathode, and also to separate electrolysis products so to prevent recombination into water. The PEM is coated with a porous electrocatalytic layer on each side. Typically, carbon platinum nanoparticles on the side that will become the cathode, and porous iridium on the side that will become the anode. The electrocatalytic layers are coated with porous current collectors. The space between each end plate and the current collector is filled with a porous gas distributor, fabricated from sintered titanium. Deionized water is then fed through one end plate, via a series of channels, on the side of the cell that will become the anode. The current collectors are connected to a direct current DC power supply. Remember that electrons always carry a negative charge, denoted by E-. Electrons flow away from the anode to the positive terminal of the power supply, attracted by its opposite charge. This draw of electrons from the anode gives rise to dissociation of the water molecule, specifically oxidation, with the water molecule breaking down into an oxygen atom, O, hydrogen protons, H+, and electrons, E-, and with the electrons lost to the circuit. Electrons flow away from the negative terminal of the power supply, repelled by the same charge, to the cathode. Loss of electrons at the anode gives the anode a positive charge. Gain of electrons at the cathode gives the cathode a negative charge. An electric field is created in the PEM between the two electrodes, with positively charged hydrogen protons, H+, flowing through the membrane, attracted by the opposite charge of the negative cathode. At the cathode, hydrogen protons are reunited with the electrons from the circuit to be reduced to hydrogen gas, H2. The two half reactions combine to give dissociation of water into hydrogen gas and oxygen gas. Over subsequent electrolysis cycles, more oxygen atoms are produced, which then combine to produce oxygen molecules, O2. Evolved hydrogen and oxygen gases rise and are collected.
So I'll stop that one there 'cause it's a fairly detailed, long video. But brilliant video showing the PEM water electrolysis process, providing a sustainable solution for the future clean production of high pure hydrogen. So once this hydrogen is created or extracted, it can be stored on sunny days when the rate of renewable electricity and, in turn, hydrogen production exceeds hydrogen demand. This stored hydrogen can then be converted back to electricity with a hydrogen fuel cell to provide a continuous renewable electricity supply, even during periods when the rate of renewable electricity production cannot meet demand. So a very useful aspect, being able to store this energy. Last video, and it's only 1 minute, I think, showing how hydrogen can be used in the steel making process, in the process called the hybrid process.
The hybrid process is considered the most promising for iron ore reduction to metallic iron by hydrogen. Iron ore pellets or lumps in the form of hematite, Fe2O3, is fed into the top of the shaft furnace. Hydrogen is heated to between 800 and 900 degrees centigrade and blown in from mid-furnace. Hydrogen rises to the top of the furnace as the iron ore descends. As the iron ore, in the form of hematite, Fe2O3, continues its descent down the furnace, it is gradually reduced by the hydrogen to magnetite, Fe3O4, to wustite, FeO, and eventually to metallic iron, Fe, which is collected at the bottom of the furnace. The flue gases from the process are simply water vapour, H2O, as a byproduct of iron ore reduction by hydrogen, in addition to unreacted hydrogen. The water vapour is condensed and exits the system, while the unreacted hydrogen is mixed with fresh hydrogen and recycled to the preheater and back into the shaft furnace.
A brilliant circular process. So this is it. This is the hybrid process again in schematic form, showing the renewable electricity at the start is used to produce the hydrogen in the first place via water electrolysis, with oxygen as the only byproduct. The hydrogen can then be stored and used in later in direct reduced iron or DRI production, producing water as the only byproduct before being combined with scrap steel in the electrical arc furnaces, powered by even more renewable electricity to produce low carbon steel. It may look ideal, but how much really does this idealism cost? HYBRIT stands for the Hydrogen Breakthrough Technology and is a consortium formed in April 2016 by three Swedish companies with a goal to transition to fossil-free iron and steel production in the Finnish and Swedish markets by 2035. The objective is to have a complete low carbon process across the entire value chain, from the mine to the finished steel. Companies called LKAB, the largest iron ore producer in Europe, will be in charge of replacing coal with green hydrogen for the DRI process, whereas a company called SSAB will convert to electric arc furnaces, and the Vattenfall will provide the fossil-free electricity required for both processes using hydropower and will develop the technology for large-scale underground storage. So a really exciting project. And all those things tied together, producing green steel or fossil-free steel. It gives, in reality, reduction of iron ore to metallic iron is not as efficient by hydrogen as it is by carbon monoxide. However, the plus side is energy savings and massive carbon dioxide savings and reductions. Energy consumption is reduced, as you can see here from the graph, by around 20%, by eliminating the blast furnace and its raw materials preparation processes of coking and sintering. The graph shows carbon dioxide emissions per tonne of hot rolled steel produced. The natural gas derived DRI route with electric arc furnace in the centre cuts carbon dioxide emissions by around 50% as compared to the blast furnace route. And then finally, the hydrogen derived DRI route further cuts the carbon dioxide emissions by around 90% compared to the blast furnace route. Current economic issues. The current production and use of sustainable materials and plans for green materials are driven mainly by climate ambition or speculation almost on their demand rather than immediate economic gain. While stakeholders may believe that economic gain will happen in the future, currently an established means of placing a monetary value on the benefits of green goods doesn't exist. Indeed, there is no widespread compensation either for higher costs that green goods entail, nor are there adequate economic barriers to non-climate friendly solutions. While interest in the idea of green materials is growing, little or no actual demand exists currently. So this lack of demand is accompanied by a substantial lack of production and infrastructure, creating a so-called chicken and egg problem for green hydrogen. Solutions are, pardon me, solutions are cost prohibitive today, but without demand, investment remains too risky for most, and for wide-scale production, that could reduce costs. And without a change in this dynamic, costs will remain high to kickstart actual large-scale demand for green hydrogen. But despite the absence of incentives for green hydrogen products in industry and the lack of market demand for these products, progressive private sector entities have been making decarbonisation efforts. Their approach is to build electrolysers within the facility using the energy carrier or creating hydrogen valleys, meaning regions where centralised hydrogen production serves multiple industries. And these cluster enough demand to achieve economies of scale, leading to lower costs and justifying common infrastructure development. which is great. They've sort of proven the technology. Um, Hydrogen can contribute to energy security by providing another energy carrier with different supply chains, producers, and markets. This can diversify the energy mix and therefore improve the resilience of the system. Drivers can include lower solar and wind energy costs, where the major cost driver for green hydrogen is the cost of the electricity. Many of the components in the hydrogen value chain have already been deployed on a small scale, are therefore ready for commercialization, and now require investment to scale up. As the share of solar and wind power rapidly increases in various markets around the world, the power system will need more flexibility, and green hydrogen can be stored for long periods. Government aims to create net zero energy systems. In total, 120 countries have announced net zero emission goals. Another driver is the broader use of hydrogen, where previously interest was largely focused on its use in fuel cell electric vehicles. Wider use includes the conversion of hydrogen to other energy carriers and products such as ammonia, methanol, and synthetic liquids. And there's interest from various stakeholders, steelmakers, chemical companies, ship owners, and airlines, as well as emission trading systems driving green hydrogen. The cost of carbon dioxide allowances reflects the price industries pay to emit carbon dioxide, incentivizing lower emissions and cleaner technologies. This graph shows the current price of around 56 euros per tons of carbon dioxide equivalent, which is expected to double to 112 euros per ton of carbon dioxide by 2040. In the meantime, this graph shows, this is from the Hydrogen Council, shows the green hydrogen process costs in 2000, 2020. Yeah, so in 2020 there on the left-hand side of the graph, and predicted progressive reduction by 2050, and compared this to the grey hydrogen as well. So we can see a stark difference with grey hydrogen costs increasing as the green hydrogen costs decrease, which is great. Policy priority. Here we can see on the schematic, the x-axis, the end uses are placed according to the estimated average daily hydrogen demand for industry, refueling stations, and combustion devices with a power relationship. On the y-axis, the end uses are placed accordingly to the differences between the technological readiness of hydrogen-based versus electricity-based solutions. And in summary, in the green areas, the high priority section, at the top there, you can see industrial processes like steelmaking, long-haul shipping and aviation, and seasonal storage, whereas electrification is likely to succeed in things like heating our homes, and this is in the low priority, the electrification section in the blue, and powering vehicles and even short haul aviation. The potential for the hydrogen economy to succeed, really. As renewable electricity grows, it can be used to decarbonise hard to abate sectors through approaches like power to gas, but direct electrification remains the most efficient and low-cost solution where possible. Hydrogen is one option among several, alongside energy efficiency, bioenergy, and carbon capture, and will play a key role, particularly where electrification is difficult, such as long-haul aviation and the heavy industries. Green or clean hydrogen can produce low-carbon fuels and chemicals and can be used in fuel cells or combustion across transport, power, and industry. However, most hydrogen today is still produced from fossil fuels, meaning a mix of production routes, including carbon capture in the short term, will be needed while hydrogen green hydrogen gets up to scale. Hydrogen in South Wales. There is a lot happening in the hydrogen sector in South Wales and beyond, with a clean hydrogen plant recently approved for Milford Haven. Groups such as the South Wales Industrial Cluster are aiming to decarbonise local heavy industries such as steel, chemicals, and cement. Whereas there are many projects or proposals in from Pembrokeshire, Swansea, and further afield. The graphic here shows a roadmap of hydrogen infrastructure, carbon dioxide capture, utilisation, transport, and storage in the region. And this was created by the this was created by the South Wales Industrial Cluster. Number of things to consider for the area. We have growing hydrogen production hubs, as mentioned in Milford Haven. They aiming to produce green hydrogen using renewable electricity, including the West Wales Hydrogen Project, looking to produce 2,000 tonnes a year, along with a 20 megawatt electrolyser facility at the port. And like I mentioned, groups and the industrial clusters. These are exploring hydrogen to decarbonise the heavy industries across the region. We've also got large-scale production opportunities, proposed projects at RWE, Pembroke Net Zero Centre Hydrogen Project. This includes plans for a 100 to 110 megawatt electrolysis plant, supplying clean hydrogen to nearby industry. Innovation and research ecosystems, facilities at Swansea University and the University of South Wales, as well as projects like the Proteum's Pioneer Electrolysers, are developing new hydrogen technologies and skills for the region. And emerging hydrogen clusters and supply chains, which I talked about in a previous slide, initiatives such as H2 Bay hydrogen ecosystem, driven by Hippo in Swansea. These aim to create business clusters, refueling infrastructure, along with supply chains supporting hydrogen transport and industry. Loads going on alongside the net zero initiatives and carbon dioxide capture as well. Why is South Wales well positioned for hydrogen? There's strong industrial demand, major energy users in industries, as mentioned on the previous slide. These could provide early hydrogen markets. There's also an excellent renewable energy potential, significant offshore wind developments planned in the Celtic Sea, and this could supply large amounts of renewable electricity for green hydrogen production. Furthermore, we've got strategic ports and infrastructure which have been extremely successful in the industrial revolution. Ports such as Milford Haven and Port Talbot provide existing energy infrastructure, import and export capability, as well as industrial connectivity. We've got active research and innovation ecosystems, as mentioned, which are developing hydrogen production, materials, and energy systems, as well as strong policy and regional collaboration between all these schemes and projects, and the UK Hydrogen Strategy supporting long-term investment and project development. There's a long list really of local companies, projects, which you can refer back to. Lots going on. And together, all these factors create a strong foundation for South Wales to become a major UK hub for hydrogen production, industrial decarbonisation, and innovation. So just to conclude, the reduced cost of renewable energy sources, combined with innovations in electrolyzer technology, is anticipated to increase the competitiveness of environmentally friendly green hydrogen. There are many challenges to upscale the various competitive electrolyzer technologies, where government worldwide support is essential for the timely achievement of viable economic solutions. The demand for hydrogen will increase substantially in the future, primarily driven as a contribution to reach the net zero carbon emission target by 2050. And hydrogen will be needed for decarbonisation as a complementary source to electrification. The evidence, well, finally then, the evidence on the climate emergency is clear, and undoubtedly hydrogen will play a part in the future of the world's energy mix. Exactly where and to what extent it will be used is not certain yet. However, it's likely that it will not be economically viable for many sectors yet, whereas for others, absolutely will be invaluable to replace the current grey hydrogen processes and to help decarbonise the heavy industries in particular.